I'll hit the record button, and then that means it's time to start. So happy Thursday, folks.
Happy Thursday.
Yeah. So did I send out an email earlier today? I meant to.
Yeah.
Excellent. We're at that point where I have no idea what I've done or said. So, yes, I read through all of your outlines. A couple of you I need more information from, or I need you to make a decision. In the cases where we need to simplify or change gears. So let me know if you can't find it, and let me know if you have questions as you progress. The next thing that I need to work on is for your, what did I call it? Check-in assignments, basically like an intermediate step. I will make that, and I will make the rubric for your presentation, and I will give those things to you. So that way you can start planning and working next week if you have free time or whenever. Let's see, I also set presentation dates based on your preferences. Let me know as soon as possible if you want to try to make a change. I was able to accommodate everyone's preferences, so I hope it will work. However, I was curious to learn that every single person wants to work by themselves. That has never happened before when I've done projects where I give people options. So that means that I needed to get 3 days in instead of 2 and some change. So I decided to remove the formative assessment that was going to be after Thanksgiving, and I'll just make the last one worth 6 points instead. Okay, so Erica and Vladimir will figure out who wants to do that later, but I needed the class time to make it work. So we'll have, the last day of class will not be presentations, it will be a discussion of that formative assessment, which I'll make longer, and then general sort of wrap up discussion, that kind of thing. So these are the dates.
Cool. Very good.
Any questions or things I'm forgetting? No. In terms of material, I will see where we land today, and you all have, let me see. Yes, you have a formative assessment that is due after I come back, so on the 27th. I will work on that so that it is posted probably by Monday of next week so that you can be working on that. It will be covering what we've been talking about. And I'll decide whether or not I want to post a video for you to watch based on how long we get, how much stuff is left over, that kind of thing. So I'll be in touch is what I'm trying to say. Yeah.
I know there's gonna be portions of next week where you are doing lots of things with family, I get that. But then also there's gonna be times when you're out at the conference. I was wondering, the days at the conference, if you would be responding to email at that time.
I will try to do email at least once or twice a day, just I won't be as,
As responsive.
yeah, as responsive as usual.
I get that, but.
Yeah, I intend to.
Thank you, thank you.
Because I can only sit and listen to so many presentations without my mind wandering. So, like, everyone at the conference is on email. Like, it seems like everyone has their laptop in front of them. I will try not to be rude to the presenters, but, you know, that kind of thing. Yes, yep. Yeah, you can, don't worry about bothering me. Just send me notes and I'll get to them when I can. That's, like, you don't have to feel like you're going to be interfering with anything. Yeah, okay. So we're talking about random slopes, right? And cross-level interactions. What is a random slope? Start there. What's the concept?
So your slope is different based upon the cluster you are in?
Yes. The idea is that there's a slope of a level 1 predictor, which is going to be a people thing in this context, and the effect of that people thing can vary across clusters. That's a random slope. That's it. So in the same way that each cluster got their own mean to start with via a random intercept, we're going to add so that each cluster gets their own slope of a level 1 predictor, and you can have that as many predictors as, you know, as your model will tolerate. The more that you add, though, the more likely you're going to encounter convergence problems. Yeah. So I made a comment to a couple of you who have small sample sizes or otherwise really complex models. Check for the error messages that show that things went awry. Because interestingly enough, and you'll see this in our example, Elmer doesn't tell you. Like the numbers look fine, and then there's just this note at the bottom that says, this broke. You know. So it is surprisingly difficult to notice that if you're not really reading very carefully. Yes.
Also, I just want to note that because of my particular data, it might pertain to somebody else. I had to use G Elmer as opposed to Elmer because of having the percentages.
Yes,
that-
the
that
binomial
and I had to
family.
use logits as opposed to other things.
Yeah. Yes, I think you're the only one who's going to end up with a generalized model.
Okay, could I
think.
do
Possibly,
something?
possibly you too, but we'll,
Well, for example, Ricardo was using my data, but I didn't know how he was using the data.
yes, yes. I think he's using it differently, but
Okay,
yeah,
well, fair enough.
yes.
But
Yeah.
me do that. Always.
Yeah, so random effects break models. There's your take home point.
Yes.
Because every new one that you add is another dimension to the iterative search process that it takes to find the best versions of these parameters. Can you have random slopes of level 2 predictors? Technically, yes, but it doesn't really make sense in the same way. So I'm going to say no-ish. So crossover with the other SEM class, random effects and latent variables are the same thing. That means factor scores and random effects and thetas are the same thing. And when you run any kind of measurement model analysis with latent factors, you get an R square for how the factor predicts the outcome. And for the same reasons that we've talked about in this class, I do not believe that is an accurate way of thinking about it. So just as random intercepts do not explain variance, they partition it into its own kind. Random slopes do not explain variance, they partition it into its own kind. Because we might know that some schools have a higher impact of the student predictor than other schools, but we don't know why. So that not knowing why makes it an error term, not explain variance, and I will die on that hill. Any questions?
Yeah, but for
Fair enough. Okay. So the object here is we are building in another kind of dependency into our model, another way that people from the same cluster can be correlated, but it's a non-constant form of dependency. So random intercept is constant, right? When you introduce a random intercept, you're saying all of the level 1 observations are equally correlated and they're correlated at the intraclass correlation. That's what that means. We're adding a random slope that adds another source of dependency that's non-constant, and it's tied to what your predictor value would be for the variable that the slope is for. So it's a different kind of dependency. It's a different way that the clusters differ from each other. It's another thing to be explained. Yes.
So if you were to try to graph random slope, would you need to necessarily, you know, fix your cluster and then show how that is going, how that's working? Or would you have all your various clusters and all their various slopes shown?
Typically, people would not plot random slopes unless it's for like pedagogical reasons,
Oh, okay.
I would say.
So for example, the
Like
right hand
this,
side,
yeah.
even though it's pretty to them for our demonstration purposes, that you probably would not see that particular graph.
No, I see it in like tutorials. You would see that kind of thing.
Okay.
Or if someone's trying to make a point of like this being a new idea that there's random slopes for this construct or something, you might have a visual of that. But generally, plots are for fixed effect predicted outcomes so that you can show what the model is predicting sort of in a more general way, not for any specific cluster. Yeah. So yeah, like those kind of pictures. It's very nice. Yes, 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 indeed. So if we want to explain random slope variance, how do we do it? That's the new part that we're adding on to. Okay, are you ready? And we'll try to go back and forth between the slides and the examples, but the data in the slides, it's not the same data set in the example. So I don't want to confuse folks. Unfortunately, that was an unintended consequence of trying to put more stuff in here. So I'm starting on slide 24 then. So if our goal is to explain random slope variance, so in this example here, I have a verbal slope right here, U2. That's the random slope because it's attached to the cluster mean centered version of this variable, whereas there's a fixed slope here that's attached to the constant centered version of this variable. Now, why do I have two different kinds of this? We talked about that on Tuesday as a new idea. Because this looks a little crazy. Why 2?
Do you have two slopes then?
Yeah, so I have 2 different versions of this level 1 predictor in the model. My question is why?
I'll answer.
Do you want?
You can predict both the
In this case, these are essentially redundant, so that would not be it. But each of them is going to play a different role. Yeah, you want to take a shot?
Okay, so the left side with beta sub 1c, you are centering versus beta sub 2c, which is where you are removing the impact of the average. So you're like centering your variables within a cluster.
Cluster mean centering, yes.
And those have two different purposes, I guess.
So because I wanted a within effect and a contextual effect, the way to specify your model to get those things directly is to use a constant centered predictor at level 1 and add in the cluster mean for it at level 2. However, had I given this beta 1c the random slope instead, I would end up with a smushed random slope in the same way that the fixed slope is smushed until you add the school mean predictor. However, adding a school mean predictor as a random slope to unsmush it, while theoretically possible, is not going to go well. So I'm not advocating for that strategy. So instead, I'm keeping the fixed effect in the way that I had it so that I create within and contextual with respect to the fixed effects, but then I'm introducing a random slope only for the within cluster part of student variable here by itself. So when you put them back together, it's still the same idea of a random slope because this is the within effect, and this represents the cluster deviation from that within effect. So it looks redundant, but it's not because they're doing 2 different things. And if this breaks your brain a little bit, do you know what I would recommend? Take this out and just use cluster mean centering, because then you know for sure everything is unsmushed on the fixed side and the random side, and you're good to go.
Contextual, you would need to do both as opposed to just the one.
If I want a within contextual version of the fixed effects, then I can't give the random slope to the same level 1 predictor because it would create a smush problem on the random side. Yep. But I could do it here, and I did. Okay. So this is our new term right here, highlighted in yellow. This is what's called a cross-level interaction because it pertains to an interaction of a variable measured at level 2, which in this case is mixed grade in this example, with a variable measured at level 1, which is constant centered verbal. So this looks a little weird if you just stare at it. It's like, how is that an interaction term? Because it's just one variable. But if you trickle this through to the beta 1 and then multiply, it works out that these 2 variables are interacting. And so gamma 1, 2 is the fixed effect that describes a cross-level interaction. In general, if you have 2 numbers here, it's a cross-level interaction of some kind. Yeah, if you have a 0 somewhere, it's a main effect of some kind, and if you have 2 numbers here, it's a cross-level interaction. Do you know why it's 1, 2? Anyone want to try to explain it? Why is this 1, 2 for the subscript? Do you want to try? You want to try? Do you want to try? No. Do you want to try? Why is it 1, 2? Okay. So it's because I left a room, essentially. So earlier in this example, I had another predictor. Let's see if I can find it. It was a way ago.
listed there.
Yeah. So there was, I already had a 1-1 in one of my earlier models. And so I skipped over it so that I didn't reuse it. So that's a odd convention that I follow that not everybody would. Let me go back. Where was I? Here I am. Come on. Yeah. So we did this part, I think, already, hopefully. Yeah. I have a vague memory of doing it. There we go. So I left room for it, but it's the second predictor of beta 1, essentially, because I tried the first one, it wasn't significant, so I took it out. But very good. Yeah. So cross-level interaction, the role of it is to explain random slope variance. So why is it that some schools have a stronger effect of student verbal ability? Maybe it's because that school uses mixed grades. So in this case, we have a model that looks like this. So gamma OO is the intercept. I'm predicting language outcomes in this hypothetical example with verbal scores on some other measure, mixed grade status for the school as well, and school mean verbal. So the intercept then is the expected language for a student with verbal of 10, right here, from a school with school mean verbal of 10, which means they would be at 0 here. So it all works out. And no mixed grades is this here. So 1O right here is a level 1 within slope, but now given this interaction term, we would say that it is a conditional slope or a simple slope. I don't like that term, but that's a common usage because it's specifically when any of these predictors in its row zero out. So this is kind of like the intercept of the slope equation. If you think about it being what happens when all the predictors go to 0. So this is functionally the within school verbal slope for schools that do not use mixed grades. That's what we have, putting that all together. The level 2 contextual slope then is the extra difference in school language per unit higher school mean verbal after controlling for student verbal. So the after controlling for is what makes it contextual. If we didn't control for that, then it would be between.
As opposed to just
In this case, 0 was not going to be in the scale of the variable otherwise, and so I centered it at 10 so that the reference school would be like someone with the middle value.
Okay.
Yep. What this number is irrelevant. It just changes the interpretation of the fixed intercept.
Well, yes.
Yeah, that's why. It was near the middle. Yeah. So we have this contextual effect here. If I want to get the model implied between effect, that's within plus contextual. So then it's the same idea. It's the difference in school language per unit higher school mean verbal, but without controlling for the students. So the extra contribution of the school is given by contextual. The total contribution is given by between. And this interaction right here is not really what we think it is. It's smushed. Up to this point, we've only talked about smushed main effects. You can have smushed interactions too. Because here's the problem. We had verbal constant centered here. If we put that in the model all by itself, its fixed main effect is smushed. Once we add the school mean of verbal, that unsmushes it into within and contextual main effects. Here, we're adding moderation of the level 1 effect, but there's no corresponding moderation of the level 2. So there's no analog of school mean verbal that's fixing this into becoming just the within school moderation as intended. So this model falsely assumes that mixed grade has the same moderating effect within as it does between. Smushed moderation, essentially, is what we've got here. Can you guess how to fix it? I need to add an interaction with verbal minus 10. Yep, this right here. That's what I need. So now I'm allowing the within effect to be moderated by mixed grade. I'm allowing the contextual effect to be moderated by mixed grade, which means I'm also allowing the between effect to be moderated by mixed grade. So now we have a parallel structure. We have a simple level 1 within slope that's specific to mixed grade equals 0. That tells me about relative within school differences across students. So for every unit higher a student is than the rest of their school, their score changes by that much. Likewise, for the contextual slope, that's specifically now to schools with mixed grades of 0. That's the extra contribution of the school mean verbal after controlling for the effect of student verbal. I can compute as a linear combination a simple between slope, which is within plus contextual. That would be for mixed grades equals 0. The new unsmushed cross-level interaction says how the level 1 within slope differs in schools that do use mixed grade, so the change to the level 1 effect when mixed grade equals 1. And now we have a new level 2 interaction, how the level 2 contextual effect differs between schools with mixed grade 0 and mixed grade 1. That implies then that we can have a level 2 interaction that's between by adding those two together. So the within interaction plus the contextual interaction gives us this between interaction. So you can get all the pieces either way. If you end up not doing constant centering, you would end up with within and between, and then you would subtract to get the contextual versions. So you'll get a chance to practice this in your last homework, which I plan to turn on very soon, although it is not due until late in November.
Thank you for lots of time.
Yeah, it's hard. It's a harder one. So, but it's hopefully going to prepare you to be able to analyze your own data, because then you will have gone through this process on CAN data where you can make sure that what you're doing is what you intended it to do. So I know this is a lot, but the main idea is that anytime you add a level 1 anything, you have to add the corresponding level 2 thing. And that's just the principle. Question? Yeah. Mm-hmm.
Do we have to make reference to the other units at that level? Because given that that's a contextual, for example, when you say unit higher school mean verbal than other schools, that than other schools to me is more similar to what we say when we interpret between cluster fixed effects at level 2.
Mhm.
Is that needed for the interpretation of contextual slopes too, or you are adding that just for reference?
I am adding, so the question was about the wording for this contextual slope.
Yes.
Yeah.
Of the contextual.
So than other schools is my way of distinguishing the effect as a level 2 thing. That holds regardless. The after controlling for the student predictor is what makes it contextual.
Okay.
And so between is not controlling, contextual is controlling. And there's a sense in which you don't have to say that, because by definition in linear models, all slopes are controlling for all the other slopes in the model. Like everything's always controlling for everything else. But I feel like in this case, the potential for the contextual between distinction to get lost is higher. So I make a point of saying it's specifically, for after controlling for student status. So.
So in level 2, beta sub 0c has the random intercept of UOC.
Okay, hang on, let me catch up.
And in level 2 at the very end.
This?
No, up one. So
Okay.
we have our U there. Beta sub 2 has a U with it.
Mm-hmm.
And just to help me understand a little bit more, why did we not have one with beta sub 1?
Because it would have been a smushed effect instead. So these two variables are essentially the same information, but they're serving two different purposes. And so I couldn't have a random slope in both because it would be the same information, but I'm having it multiply this version to ensure that the random slope represents only heterogeneity across clusters and the within effect. Yes.
Thank you.
Well, let me go back a couple slides to show you what the simpler version of the model is, just to do a comparison. This is slide 15. So in this version, I am using cluster mean centering, and so you can add the random slope directly. So if you use cluster mean centering for everything at level 1, then this weird, the fixed slope is here, the random slope is here thing is completely avoided. So in this version of the model, we have within and between fixed effects. The within effect has a random slope, and this would be a cross-level interaction here, this 1, that says how the within level slope changes per unit of this level 2 variable in that case. So it's the same type of interpretation as a normal interaction. In cross-level interactions, it's usually the case that the level 2 variable is thought of as the moderator and the level 1 variable is the predictor, but not necessarily. You could also talk about it as how the effect of cluster mean whatever changes per unit of within cluster whatever. You could go that way too. Sure. So here's the version of the model where I didn't skip over the numbers. This is the earlier version. I have a gamma 01 and a gamma 11 for homework and the cross-level interaction of homework with within student verbal. So here are some numbers to look at. The new terms are highlighted in yellow here. So we had previously tested whether U1 is needed in this example, and it was. And if I add a random slope, what also am I adding simultaneously that's not on the slide in terms of the notation? Do you remember? If you add a random slope, you're not just adding its variance, you're adding one more thing. Do you think that a school's intercept and a school's slope should get to be related? If they're both from the same school? Yeah, we wouldn't want to do that. So anytime that you're adding a new random effect, a new variance for it in particular, you are also adding covariances with the random effects that were already there. So if you go from a random intercept to random intercept plus slope, that's a change of 2. 1 for the new slope variance, 1 for the covariance. If I add a second random slope, I've added 3 things because I have the new variance and then the covariance with the 2 random effects that were there already. So that's not in this version of the model because covariances do not contribute to predicted values. But if you express this in matrices, then you would include a covariance between these 2 things as part of that representation that builds the variance structure. So in this case, let's practice interaction terms. Should we do that? It's always fun. It's one of my favorite things to do and teach. It really is. I love interaction terms. Within cluster verbal, okay, that's going to be the slope that we care about. In schools with more homework, what happens to that slope?
Becomes less positive.
Yeah, less positive is how I would say that because the slope of verbal is 2.4. The interaction term with homework is negative. So that means as homework increases, the effect of verbal becomes less positive, meaning weaker, towards 0. How about for schools that have mixed grades? Yeah, it's stronger by 0.3 in schools that have mixed grades. And the fact that this interaction is, we'll call it significant, it's 0.04. Yeah, it's fine. The fact that it's significant means that there's a difference in the effect of the within cluster verbal between those. How would I get to what it is in schools with mixed grades? What's the model implied slope given the interaction term? How do I get there? If I asked you a homework question, right? What is the effect of within cluster verbal in schools that do not have mixed grades? It's right here. What is it in schools that do?
It's that plus that.
Yeah, this, what it is in the 0 group, plus how it differs in the 1 group. So it would be the sum of these 2 numbers right here.
No, because 0.
If it's a school without mixed grades, then yeah.
without-
Yep, so then it would just be this part by itself. More generally, your simple slope is found by starting with whatever the main effect slope is, plus the interaction times the value of the moderator you want the simple slope for. So I would plug in a 1 times this interaction term because mixed grade goes to 1 in that category. If I had a quantitative variable, such as, let's do the last one here,
Centers?
this is
Five or centers?
This is among the two parts of the variable. So this is what I call an intra-variable interaction beyond just cross-level. So this, I don't care about the p-value, I just want you to know what to do with the numbers. So what's the pattern here? In schools that have higher mean verbal, what happens to the effective student verbal? The interaction term is negative. Yeah, it weakens the effect. So then we would say that in schools where everybody has strong verbal, you having relatively stronger matters less. And I think that's a reasonable thing for a lot of these variables that you're splitting into pieces, so that the effective variation depends on sort of where you are on the scale. There can also be caused by ceiling and floor effects, that kind of moderation as well. Yes?
Is that now that do you think that a proportion of something that goes between 0 and 1, the estimate, and at level 1 you have something like a score in which 1 unit difference can be, well, the score can be between 0 and 100. So what unit difference means in both predictors is very different. Do you think that that can be a problem for cross-level interactions, given that they are trying to capture what one unit difference means in both predictors at the same time?
So the question was, what if the level 1 and level 2 predictors have very different units, such as the level 2 is a proportion that ranges between 0 and 1, and level 1 ranges between 0 and 100 or whatever? No, it's not a problem. I mean, that's the short answer.
We're just doing a product of interactions and make a prediction.
I think communicating it is the problem. Especially because people want to look at a slope and be like, oh, look, this is 3, and that means it's a stronger effect than this slope that's 2. And it's like, you're talking about effect size. You got to keep the units on there. So I think if you forget the unit part, then it's a problem. But so as long as it's like, this is per this is per this, like you keep the units with you, then you're in, okay.
They're probably based like compared to the base model or compared to like thin cluster verbal moderated by mixed grading.
Okay.
Significant. Is that significant compared to a thin cluster variable or compared to like the empty model, like the base?
It's not through a model comparison, it's through a Wald test. So I'm not sure if I understand the question.
Like, I just don't like, is it saying that it's significantly different compared to if it wasn't moderated, or just adding that significantly different compared to a model without that?
This contributes uniquely. So the model would be significantly worse without it. But you couldn't do that comparison via a likelihood ratio test because in RIML, you have to keep the fixed effects the same. So T or F are really your only choices for comparing fixed effects across models. But without this term, then this would be holding for both mixed grades and not mixed grades. And so then this number will change as a consequence of it being redefined to be specific to group 0. Is that better or no?
Yeah, I'm just making like, so like that shows just within cluster verbal alone is significant. Like it is significant to your model, but is the moderating effect like, I guess, is it significantly different from just having that without its moderate? Like,
well, this verbal effect is not the verbal effect. We have to remember that it's specific to schools that have homework of 2, that do not have mixed grades, and that have an average verbal of 10. So this slope being significant or not is only one of like an infinite number of possible slopes that this model implies. If you're interested in sort of like what is the average slope across all these, then you can get that with something called, it's in Stata, it's done by margins. Marginal effects, actually, that's what it's called. I'm sure you can find that in R somewhere as well. And essentially what it does is, like, for every school in the data set, it figures out what that school's slope would be based on its pattern of these moderator variables, and then it averages over those within cluster slopes to get what the average one would be. That way, the relative imbalance of values across these predictors is taken into account in computing that average as a weighted average rather than an unweighted average. So that might be more useful to you if you want to know that. But the fact that this is significant would mean that this effect wants to be different between the two different types of schools. I don't know if it would still be significant if you didn't have these other two interaction terms in the model, but I would assume probably. Okay, am I getting anywhere near the answer? Yeah. I'm trying. Can I get credit for trying? Yeah, thank you.
Good partial credit.
So this version of the model is a lot less convoluted. Can we agree? This is going to be easier to explain. It also makes it easier to infer which of my piles of variance these three new cross-level interactions should have explained. The rule that I told you on Tuesday, remember that? It explains the term that's in its equation. That's the answer. So anything you stick in at level 1 explains E. Anything you stick in as a predictor of beta 0, you're saying it has a main effect. That explains U0. Anything you stick in here as a cross-level interaction would explain random slope variance. So in the unconditional slope model, we said gamma 1O is the average slope across all the schools, and U1 is how far off your school's slope is from that average. Now we are saying that schools get a different predicted slope based on their homework status, their grade status, and their school mean verbal. And to the extent that these things matter, we should see less U1 random slope variance than we do before. And this is how much it explained, 0.04%.
So if you had a perfect job with your other predictors, it's okay that would be 0. If the random slope intercept was 0, yes?
You mean the variance of the slope goes to 0, or?
What you just mentioned, if we had that, if that was 0%, that's not necessarily a bad thing.
It just means that these effects are tiny. That's what I would say.
Okay.
So cross-level interactions are designed to explain the random slope variance for this predictor's effect. That's what they're for. So that's why we would always want to test for a random slope in the first place, because that's what these are for. So if that's not in the model, then we're going to have a problem potentially. There's a specific use case in which that might be okay, and that's later in the slide deck, but this is all I'll say for now. All right. So then when you have constant centered level 1 predictors, all is well. If you want to have the constant centered version so that your fixed effects become within contextual, that's where we started with today. So let me go back to that then. So we would end up with a smushed random slope if it multiplied the original variable instead. So this would be the baseline model, where we have just the new random slope for the constant centered variable. And so then this is U2 because it's multiplying a different one, whereas the fixed slope is going with the first one. And U2 variance in this model represents a new baseline for a point of comparison, because this is all the random slope variance that there's going to be at this point, whatever variance is estimated across these U2s. And so then the question is, what reduces it further? So the composite notation, then here's an example of what that looks like if you don't write out with the beta placeholders, you just put the fixed and random effects in directly. And in some cases, this can be easier to understand. So this is what it looks like in code. And then we have an example here. So I do want to point out just in this, what would happen if we use different versions of the predictor for the random slope. So if I used the constant centered version that's on the right, I get a variance of 0.1996. If I use the cluster mean centered version on the left, I get a variance of 0.224. So it's a different number. The smushed one over here is closer to 0 most likely because we're assuming that at level 2 the same pattern of quadratic heterogeneity holds across the cluster mean as holds across the level 1 version of the variable. So it's like that 0 is pulling it. Smushed. It's still this.
Yes.
But if I do this for fixed effects, I feel like I need a new gesture for random. Maybe we should like go sideways or something. Anyone? No? No, nobody? Okay, well this is fixed. It's the same problem.
Smush this.
Yeah, and I feel like one of those like, 80s dance videos or something. What is that, the robot? Yeah. All right, so then we want to avoid smushed random effects. That's the thing here. Let's see. How we do that then? This is where we started back again here. So now we're adding a cross-level interaction with the level 1 predictor so that we end up with within and contextual effects, but only adding it here smushes that interaction term. So we would need to pull in the interaction between the two, the cluster mean with my moderator as well. And this is what I would call a level 2 interaction because it's among two level 2 variables. Which variance component should it explain? This new level 2 interaction. Which level 2? There's 2 U's here. Yeah, the one that's in its row is the answer. Yes, indeed. Exactly. Do I have data? I have data. Yeah, so homework 2 was not supposed to be in this model. That's why here. That was where the 1 went. So I just cheated and just took it out there. It's not in here anymore. It's fine. It's fine. So we end up with 2 different versions of the model here based on how you've centered it. So actually, no, depending on whether you've smushed it, that's what this one is. So the smushed model is over here on the right without that new level 2 interaction, but with the cluster mean. So 0.37 is the interaction term estimate, whereas after we unsmush it, the within version becomes 0.34 and the contextual version is 0.4. So to add those two together would be the between version. So this model on the right says that the effect of mixed grade in moderating the slopes is the same for the within slope as the between slope. The model on the left that adds this interaction says it is different for the within and the between, and this contextual interaction is that difference. So again, big picture, anything you do at level 1, you got to do at level 2. If you're using constant centered predictors. If you're using cluster mean centered predictors, you don't. There's no danger of smushing in that way. Anything you leave out is assumed to be 0. It's not assumed to be the same as something else. Okay, so this. Then if I do the non-hybrid version and just simplify that way with cluster mean centering, then I end up with within effects and between effects. I can still find contextual effects and contextual interactions. So then it's a subtraction rather than addition, but it's the same deal. Okay. Here is how those would map onto each other. So again, switching out so that we only have cluster mean centered predictor at level 1. So if I have that new version on the right here, I end up with the same level 1 interaction, but different level 2s. This is the between version, this is the contextual version. So these two added together gives me that 7. And so as a linear combination, I can get the model implied main effect that I'm missing. Between over here is what I'm missing. Contextual is what I'm missing over here. So then in English, I have interpretations at the bottom here of slide 31. We would say that the within verbal slope is stronger by this much in mixed grade schools. The between verbal slope is also stronger by this much, and the contextual is this much too. So the effect of moderation is after controlling for moderation at level 1, in the same way the main effect of a contextual slope is after controlling for the predictor at level 1. Same deal, just same idea. Same model for the variance either way. So I have here. All right. Do you want to talk about free lunch? Michael's offering his lunch for free. There you go. You got to finish your spaghetti, dude. It's going to get cold. It's already cold. Cold spaghetti. Yeah.
It's like cold pizza.
Cold pizza is always good. Cold spaghetti, I'm not so sure about. Although, I would say like certain kinds of noodles are good cold, so I don't know. I have to rethink that. Question or comment?
Question is
Yep.
what happens if I have one list of resistance and I know level 2, and I know that potentially that mean at level 2 could interact with the level 1 variable. That could be a thing. For instance, in research, we know that we have a gap between males and females in, let's say, math scores, standardized math tests. And we know that the proportion of females in the school can be something, and we know that that proportion can affect the gender gap.
Mm-hmm.
In those cases, Lisa, if we want to add a cross-level interaction between the level 2 and the level 1, does it mean that we have to add like a quadratic effect at level 2?
Mm-hmm. That's where we're headed. That is where we're headed. Yep. Yep. So I will. Do I have that? Let me see here. I know I have slides about that. I didn't know if the thing I'm thinking of is in there though. 1 second. Yep. Let's just do that. 2 slides. What he just said. Okay. No free and reduced lunch just yet. We'll stay on this one with language. So if you wanted to see if the level 1 effect of having more of this predictor than your peers, so in this case verbal ability, depends on how much ability your peers have. So we're talking about an interaction between the 2 parts of verbal in this model here. So we have level 1 verbal interacting with level 2 verbal. However, this has the same potential for a smushed interaction, because before we added mixed grade times school mean verbal, this cross-level interaction was smushed. It said that the within effect and the between effect of verbal were moderated by mixed grade to the same extent. Okay, we solved that problem by interacting our verbal at level 2 with the same moderator. Whatever you do at level 1, you got to do at level 2. So in this case, this is smushed for the same reasons. So how do we fix it? Whatever you do at level 1, you do at level 2. It actually turns into a quadratic term. I know, it breaks your brain a little bit. I can explain this a little more simply though, or I can try. Don't worry, I'm not going to draw. We're going to get Excel out. Nobody wants that. Okay. So if we have our level 1x and it's been centered at whatever, and we have our level 2x, and we add that in. So at this point, we have a within slope, and we have a contextual slope. Oh, no. I had a within slope. I know. Can't type in front of people ever. Contextual. Okay. Now let's say that we want to see if the within slope varies by some moderator. Okay. If I just have that, what do I have here? What kind of effect? Your choices are within, between, contextual, or smushed. This is smushed.
Until you tell if you don't know.
Right, so just at this point, there's nothing in the model that tells us that the level 2 part of this variable should have a different moderation than the level 1 part, because this is the original variable. So we fix it, right? And so once we put that in, we end up with the same idea here. So are we good so far? Okay, now let me break your brain. What if my moderator is level 2x? That would translate into level 1 times level 2x.
Oh.
Really? I can
You're
type.
doing that.
My computer's like, no, they don't want to see this. Just stop it. If m is level 2x, then you end up with the quadratic term. It's crazy looking, but this unsmushes the cross-level interaction.
So, if this was your model, would you need to list all 6 of those? Or would you only go with the J column for identity context? And then the 2 that you just highlighted?
You can have as many of these things in your model as you want.
Right, no.
but-
I just meant though, so if M was level 2, as you've indicated.
Yeah, like the moderator in this idea is the
It
level 2
is the level 2.
part.
Do we need to have the 5 in the row 5 and 6? Yes?
Well, this would be a different variable.
Okay,
Like if this is mixed grade or something,
right.
right? Like that, this seems like it's easier to understand than if we try to do the intra-variable interaction, because it results in a quadratic effect being needed to unsmush it. But not if you don't. If it's cluster mean centered, then you don't have to have this. But this would be how the between effect is moderated at level 2, and this would be how the within effect is moderated instead. Okay. So yes, Vladimir, that's where we're headed. Thank you. So we did this last time at the end of class. I think we can do it. You want to look at it very briefly again? Random slope and then add cross-level interactions. Also, we are going to have a visitor at the end of class today for a few minutes. There's some sort of data model, like activity competition thing that the university is throwing, and I got an email from someone saying, hey, can I come pitch this to your classes? And I said, all right. So someone is coming soon, I think.
If they throw candy.
I don't know if they're of that kind, but we'll see. So I'll talk until that person gets here or else. So random slopes then, and because this model, so we're back to free and reduced lunch, this is phrased as the binary version at level 1, because almost always that's what people will do in practice. It's very difficult to wrap your head around decimals in terms of differences. Cluster mean centering is weird for binary predictors. So this is a binary predictor. So I'm setting this up as a hybrid model where the fixed effect is with the original binary predictor, the random effect is with the cluster mean centered version, just like in the slides I just showed you. So in Stata, I'm adding a random slope here. So note the 2 different variables. The fixed is the original binary version, the random is the within cluster version. And also in Stata, you have to ask for it to estimate covariances among your random effects. That's not a default. So cov_un is the command that will do that for you. In R, it is a default. So in the corresponding R code, same deal. The fixed effect is given to the original binary level 1 predictor. The random effect is given to the cluster mean centered one instead. And R automatically adds covariances among random effects that are inside the same parenthesis here. So if you wanted to shut that off, you'd move them to different parentheses, as far as I know. I think there's something with a bar maybe, like that shuts it off or something. Vladimir, have you seen this before? Erica?
Yeah, but
Something like that. Okay. Yeah, there's other ways to shut it off, but I know that putting them in separate parentheses is one way to do that. So that would be the easiest way. Let's see here. We'll look through this. So our new slope variance is 14. Our random slope is correlated with the random intercept negatively at 0.5. So that means that schools that have a larger slope have a lower intercept in this case. Actually, no, let me take that back. These slopes are negative. Okay, so I got to do my arm here, right? So the best case scenario is a school where there's not much difference as a function of free and reduced lunch. Worst case is there's a big difference. So in this case, if you think about the slopes as a column in your data set, a high value of the slope is one that would be close to 0, and a low value would be a very strong slope. So then if you think about the intercepts as a column and what a negative correlation would be, that means as you go up on your intercept, you go down on your slope, which means the highest means are associated with the strongest slopes because the slope is negative. Did that hurt anyone else's brain? That hurt a lot. So I have, where's the interval? Here's the interval. So computed a 95% confidence interval using the fixed slope as the midpoint and then using the square root of the random variance for that slope. So 2 standard deviations essentially. So then higher intercepts go with lower slopes if it's a negative correlation, which is actually a more negative slope if you think about it on the number line. So I think that these kinds of intervals are useful for conceptualizing what the slope means. Like, is it a difference in the size of the negative impact? Is it a difference in the size of the positive impact? Or is it both? Like, is it spread around 0? So this now represents a second way that clusters differ from each other that we get to explain. All right, So then I have code here that does various things to help compute effect sizes. So one important thing that I want to make sure folks are aware of is that we do not compare back to the empty model anymore. We've added in a random slope. So when you're computing pseudo R-squares, the sequencing can be very tricky. In this case, I'm not comparing back to the empty model because that model only had 2 variance components. It had a random intercept and it had a level 1 residual. Well, what we just did is, after explaining some of that variance with our fixed effects, we separated out what was part of the residual and put it at level 2. So that residual from the empty model or from the previous model doesn't mean the same thing. It doesn't have the same information in it. Likewise, this intercept is now conditional. Do you remember how it changes once a random slope is included? Before, this was just the random intercept period. Yeah, parallel lines. But now, in the same way that the fixed intercept is just the mean period, and it becomes the expected mean specifically when the fixed effects zero out, this is the expected intercept when the random effects zero out. In other words, for a student who is at their school's mean for this variable. So this is an intercept that's conditional. It's the spread at that point. And I know there's a picture of that. Let me get the picture. Come back. Lost my mouse. My favorite colored picture. Yes, this. Trying to convey that if I had 0 as a value right here, I would have a different random intercept variance than if I had 0 as a value out here. So it's a different interpretation, it's a different number, and so for those reasons I don't believe you can come back to it. So at this point, then, in the analysis, my goal would be to explain the new cross-level interaction. Why is it that some schools have a gap of up to 15 and other schools have a gap of only 1? That's what we might want to know. So in the next part of this, after our results, I am saving the numbers from Stata and R here to, this is all Stata code to start with, so that I can have these variables to compare against to do pseudo R-squares for the subsequent models, because this is my new baseline. So I saved these variances out of R, or Stata, excuse me, and then I can refer to those things here. and all of the computations for confidence intervals, reliability, and so forth. In R, I did the same thing with the var_core function and just asked it to go in and use those values as they were. I didn't bother to save them. All right. So one of the reasons why schools may differ from each other in the size of their lunch gaps is school composition. Does it suck more to be poor if you're in a poor school or a wealthy school? That's my question. Yeah. So I'm adding in, beyond the two main effects of this is paid for lunch versus reduced or free as the binary variable, this is the mean of that variable across schools, so it's the proportion of students who get discounted lunch. I am now adding in an interaction term. So that's a hashtag in Stata, computing effect sizes. It is a colon in R, because I already listed out the main effects over here. What do we think? So now, 50 is the expected math score for what kind of person and what kind of school? Go down the list.
It's a, that's 0 out, so it's
Yeah.
the person that is not receiving free lunch.
Yep, they pay for lunch. That's what the P
Pay
stands for.
lunch.
Yep, they pay for lunch. What kind of school do they go to?
The 30% of the students receive the reduced lunch.
Yep, 30% get a discount at lunch. Yep. So this is now a simple slope because of this interaction term, as is this one. So then this value of the lunch gap at the student level, students who get a lunch discount are lower by 8 points, specifically when the interaction term drops out, which means they go to a school where 30% of the kids get discounted lunch. What happens to this deficit in schools with higher proportions of discounted lunchers? Less negative, less bad. So there's less of a gap between the haves and the have-nots, the more have-nots there are. Less of a gap between the haves and have-nots, the more have-nots there are. Likewise, we could talk about the effect of school composition and how that changes based on which kind of student you're talking about. So for every unit of this variable, math goes down by almost 19.
But that's 0 to 100%, which is 0 to 1.
Yep, so this is the change from schools that have no discounted lunch to 100%. So this would be where I divide by 10 and talk about, for every 10% more poor kids, your expected math score for that school goes down by 1.8. And in kids that get discounted lunch, this level 2 effect is reduced. Same pattern. However, do you see anything wrong with this model? Is this interaction term referring to moderation of the within effect, the contextual effect, the between effect? Yes. Yeah, this is a smushed interaction. We are assuming that school composition moderates the effect of lunch equally at both levels. So this is an example of this situation right here, where to fix it, we need the quadratic. Which variance component should this cross-level interaction have explained? It's level 2, but which one? I got 2 of them here. That one or that one? Intercept or random slope? 50-50 shot. Yeah, it should have explained the random slope. So part of the reason why schools differed in their lunch-related deficits could be school composition. It's supposed to be explaining the random slope. So we should be able to see that if we computed pseudo R-square. And indeed, we do. About 6% of the slope variance is attributable to school composition according to this model. Random intercept went up a little bit. Actually, no, because it goes up if you explain residual variance at level 1. It can wiggle a bit if you, but they're not tied together in the same way across levels. Yep. But we can fix it, right? With this new term right here, squared. Why is this gamma O2? Yeah, so the ones in this row all start with 0 because they're predicting beta 0. This is the second predictor of beta 0. Likewise here, this is the first predictor of beta 1, so it's 1, 1. Then I also have a note down here about the model implied between slopes. So if I wanted to get the main effect of free and reduced lunch, I can add together the within main effect and the contextual main effect. If I wanted to get the between by lunch moderating effect, I can add the within this cross-level interaction, moderating the within, to the one moderating the contextual. Then I end up with between. So it works the same way as for the main effects. Maybe he forgot. I don't know. We'll find out. Code. Output. So this is one of those things that I added a quadratic here in R, and I wanted it at the end because it was the newest term and it wouldn't let me. So, nah.
You want to keep your quadratic and not
Yeah, I mean, it reorders things. So I've had times where I put like 2 main effects and then their interaction, and then I'll add other main effects, and it comes out all in the wrong order. Like it decides that. So just watch that when you're building your contest 1D statements with the ones and the zeros. It has to be the order it thinks it is, not that you want it. Yep. Okay, so now we have a slightly different story. That's within moderation. This is contextual moderation. So we have a separate estimate. And in this case, it looks like that's not significant. And after controlling for that contextual moderation, the other cross-level interaction is not significant. How about that? All right. I don't know if the person's going to come or not. I'm going to pause for a second. Homework 3. Yes, you could get pretty far into homework 3 by now, I would say, but we're not done talking about this yet, by far.
like I said, I like the homework because that's the pull together for me.
That is the intent.
Well, but I'm
Yeah.
saying that just
Good. All right, then I will be in touch regarding when stuff is open, available, posted, all that kind of stuff. I'm not here next week, but you can email me. Office hours next week, right? Got that plan?
this
This room is closed on Thursday, so office hours on Thursday will be on Zoom, but office hours on Tuesday will be hybrid, right? You're going to be on Zoom, is that right? Yeah, and then Vladimir's going to be here, I think. All right, we're not doing office hours. Am I getting confused? No, never mind. That's the other class. Scratch everything I just said. There is nothing happening next week. There. You guys are off too.
what?
Yeah, Vlad, he's going to the conference, so yeah, he's not holding office hours. No, so yeah, I just got confused. I'm sorry. I'm a little scattered at the moment, so I'm right there with y'all if you're thinking that everything is like too much all at once. That's where we're at. All right, let's pause there. Let me know if you need anything. I'll be in touch. Otherwise, I will see you on the other side on the 28th. All right. Thanks for being here, folks.